In this unit, we're going to investigate temperature and heat, and we're going to understand what changes when temperature changes and what causes temperature changes. So the first thing to understand is that temperature and heat are actually very different things. So we are aware of temperature because we reach out and touch something and we say, oh, it's hot or it's cold. And what we're doing is we're giving a relative indication of how hot or cold it is. And that's usually how we define temperature, a relative measure of hotness or coldness. But I actually want to know what it's physically connected to. What is making something hot or making something feel cold? Well, temperature is actually dependent upon the random translational motion of the atoms or molecules that make up matter. Now, if it's a single monatomic gas, like say neon or something, then this is a fairly straightforward thing to do. But almost all matter is very complicated about the relationship between temperature and particle motion. We're going to look at that in a little more detail. Translational, remember, means linear. It doesn't have to be a straight line, but it is moving from one point to another. So temperature, the faster these particles move, the more kinetic energy they have and the higher the temperature will be. Heat, on the other hand, is not contained within the object, but rather can flow between objects. Heat is the flow of energy between two objects due to a temperature difference, and you're familiar with heat flowing from hot objects to cold objects. Heat is a lot like work. You remember from Physics 1 that when you have energy, you can do work, and that work transfers energy to another object. Objects do not contain heat, they contain energy, but energy flows out of them as heat, and that heat can be absorbed by something else, and then that object gains internal energy. So, what do I mean by internal energy? Well, that's interesting. Internal energy is the total energy of all the particles that are in an object. So when an object takes in heat, its internal energy increases, and that results in more random motion of particles within the object. So let's consider an object that's made up of two different atoms bonded together. Okay, so or maybe same atoms bonded together, like oxygen gas is two oxygen atoms bonded together. Their translational motion means this whole thing is going to move along some path, and that's what we're kind of measuring when we're measuring temperature. It's random translational motion. But this thing also has some other things going on with it. These two oxygen atoms, they're bonded, but that bond can stretch like a spring and it can contract like a spring. So what we have here is vibrational motion between those two atoms bonded together. Heating it up can cause that vibration to increase. That's part of the internal energy. This thing can also spin along multiple axes. It can spin in circles, it can spin in circles, it can spin in circles. Okay, so the rotational motion is also part of the internal energy. Translational motion, rotational motion, vibrational motion, plus there are intermolecular forces of attraction between these two oxygen molecules, which means there's even potential energy there. So all of those things together add up to give it the internal energy, the total internal energy of the molecule. Okay. We're not going to get too worried about that, but when we are trying to figure out what internal energy is, we are talking about all of those different things: rotational, vibrational, translational, and potential energy between the molecules. When we're measuring temperature, we're really only measuring one piece of that. We're really only measuring the random translational motion of the particles, or temperature is related to the random translational motion of the particles. Now, we still need a scale for temperatures, so if we're measuring these things, how do we make it anything but arbitrary? Well, a temperature scale starts with reference points. So we use a thermometer, and the thermometer changes based on a change in temperature. Usually something expands or contracts because of a change in temperature. We call that thermal expansion. Okay, and thermal expansion refers to both the contraction and the expansion. A contraction is simply a negative expansion. Usually things when cool down, they contract. When they warm up, they expand. That has to do with the motion of those particles like we were just talking about. So what we do is we take something that we can use as a reference point, and then we figure out the volume of say a thermometer at a certain temperature. We go to another place and we say, okay, well, here's where it's at here, and then we divide it into parts. This is easier explained with a animation. So let's say we take water and we take a temperature, a thermometer, which is a lot of times just a tube with a bulb on it. It's sealed and filled with some liquid. So we put a liquid down here and we take this thing and we put it in Ice water. Ice water has a known temperature. It's always the same. We call it 0 degrees Celsius or 32 degrees Fahrenheit. And that's actually our very first part of our scale. So we take this thing, we put it in water that's just right at the ice water melting freezing point, and the liquid will be some height in there. So we're going to call that 0. Unless it's a Celsius scale, then we call it, or sorry, a Fahrenheit scale, then we call it 32 degrees Fahrenheit. So 0 degrees Celsius equals 32 degrees Fahrenheit. Then we're going to take and we're going to heat this water up. This is my fire. We're heating this water up. And that's going to cause the alcohol inside this thermometer, or mercury, or whatever it is, to expand up to another point. And so when the water starts boiling and steaming, it gets to that temperature and stays there. If the alcohol has risen to this point, okay, we can give this whatever number we want. And the Celsius scale says let's call it 100 degrees Celsius. The Fahrenheit scale says let's call it 212 degrees Fahrenheit. So here's two temperature scales. This is 0 degrees, this is 100 degrees, this is 32 degrees, this is 212 degrees. They're exactly the same thing because we use the exact same reference points. And so if we said this is 100 degrees difference between them, then we just divide this length into 100 equal length divisions, and that gives us a degree change of 1 degree. Now, since there's 180 divisions between 32 and 212, turns out a change of 180 degrees Fahrenheit is equal to a change of 100 degrees Celsius, which actually is useful for us so we can actually figure out the relationship or how to convert between these two things. So we have multiple temperature scales, we need to be able to convert between them. So to do that, an easy thing to do is just create a graph and find our commonalities. So down here, I'm going to put Celsius. Okay? And I'm just going to list Celsius from here's 0 degrees, here's 100 degrees. And over here I'm going to put Fahrenheit. And I'm going to start at 32 and I'm going to go to 212. Now the line 0 and 32 are the same. There's a point. And the line 100 and 212 are the same. There's a point. So if we can actually find the equation of this line, F equals mx plus b, except x is really c for Celsius. So this is the equation, y equals mx plus b. M is slope, F is our y value, our degrees Fahrenheit. C is our Celsius value, degrees Celsius. B is our y-intercept. Well, we can look at this right away and we can see, okay, well, degrees Fahrenheit equals our slope. Well, what's our slope? Well, this thing went up 180 and it went over 100. Well, 180 over 100 is 18 over 10, or 9 over 5. So 9/5. Our degrees Celsius is just our variable, degrees Celsius, plus our y-intercept, 32. So what we take is we have degrees Fahrenheit equals 9/5 times degrees Celsius plus 32 degrees. Now, if we wanted to do that the other way, we wanted Celsius to Fahrenheit, then we just solve this for Celsius. So we're going to take our degrees Fahrenheit minus 32, and then take that whole quantity times 5/9, and that gets us degrees Celsius. So we can convert from Fahrenheit to Celsius because we understand how the scales were derived, not because we're memorizing some kind of formula.